Prevalence of the mobile device usage, including the smartphones, tablet, and also the smart IoT devices, smart home appliances, inevitably make these devices contain private and sensitive information. However, the unauthorized access to these mobile devices will put these devices under high risk of misuse. And to defend against this unauthorized access to these mobile devices, traditional approaches, including the passcode and the graphic pattern. But these solutions actually usually suffer from the passcode theft, shoulder surfing, and also the smart attacks. So the biometric-based method provides a new pathway to secure the mobile devices, such as the fingerprint sensors were equipped on some premier smartphones. But there is a large market, actually, especially in the developing countries, they're not equipped with these fingerprint sensors. So the researchers seek for alternative solutions utilizing these cardiac biometrics to facilitate the user verification. These solutions mainly rely on the body-attached ECG or PPG sensor, or even using the Doppler radar to extract the unique biometrics, cardiac biometrics. But this solution also have some limitations. They will add some additional cost and also will bring some inconvenience to the mobile users. So a practical solution is urgently required. So our method, cardiac camera, actually is low-cost general user verification systems can extract these unique cardiac biometric features. And also we demonstrated that this intrinsic, unique, and non-violational cardiac properties can be preserved by utilizing the built-in cameras on the smartphones to capture all the reflected light on your fingertips. And also our system robustly can verify the user and reject the spoofing attacks in which the adversary are trying to pass this our verification system by place their own fingertips on the camera lens. And also our system have a very low requirement on the hardware, which we believe that our system can be applied to a broader array of applications or services where there is a need for the user verification. The basic idea of our system is that we just simply ask the user to put their fingertip on the built-in camera, and with the flashlight turned on, it will illuminate the skin of the fingertip, and the built-in camera will continuously monitor the light absorptions with the built-in camera, and then we will derive the cardiac wave directly from the light intensities of the frames we recorded. And now we know how we can derive this cardiac wave, but can we utilize this cardiac wave to verify users is still a question. So before we get down into our system design, let's first review briefly about the kinetics about the cardiovascular systems in our human body. The heart will continuously pump the blood into the vessel, and through alternating contraction and relaxations, which will form a periodical pattern. Usually we call the cardiac cycle. And the vessel will carry the blood circulate throughout our body, including your fingertip. And there are four major phases in the cardiac cycle. Due to the physiological difference of the cardiovascular system, people, including actually the heart size, heart shape, and some tissues on your heart, actually people will exhibit different cardiac motion patterns, which actually indicate the unique cardiac biometric features we can utilize to facilitate user verification. And the built-in camera can continue to capture the blood flow variations by measuring the intensity changes of the video frame. And the figures on this slide shows that will confirm the uniqueness of the cardio feature. The idea of our system looks very straightforward, but there are still several challenges we need to address before we start to design our system. First, the cardiac motion patterns are very easily impacted by the ambient light conditions, and also it's essential to design reliable features extracted from the cardiac wave that can mitigate the impact from the ever-changing the fingertip press position and pressure. And also, it's the heartbeat actually always affected by the human movement and also emotion status. So let's come to our system design. I will first talk about the overall picture about our system. First, the data acquisition system is first initialized with both the built-in camera and the flashlight turned on by detecting the camera, whether the camera is covered by a fingertip. And then next, we design a gradient-based optimization techniques will adapt the camera configuration, which include the flashlight intensity and the ISO to mitigate the impact of the ambient light condition. Next, the reliable cardiac motion patterns is derived with module dynamic cardiac wave extraction from the captured video frame. Since the pressure position and the pressure of your fingertip are always changing, have slight changes during the verification process. So we also developed dynamic pixel selection techniques. We're using to select a set of pixels on the video frame we captured that was most sensitive to the blood flood variation. And based on the cardiac wave we extracted, and then we also derive 30 systolic and diastolic features based on the raw cardiac wave measurement, and then through some further processing, we further extract the 36 non-fiducial features to combat of some other environmental changes during the verification process. So next, given all these extracted features, we will match all the newly captured cardiac wave, cardiac biometrics with a predefined user profile. But instead of directly using this cardiac wave, the morphologistic features we extracted in the previous module, actually we will design a feature transformation scheme or convert all these features into a set of robust feature abstracts through the primary component analysis. Finally, we will give the your verification results. Then next, I want to go through each of the components in detail. First, for the fingertip touch detections. So in our operation, we found that when the camera lens was fully covered, the frame we captured will be dominated with the red channel. And also in these frames, the red channel will have extremely high intensity. So that's, we're giving the examples shows here. You can see that if the camera lens was fully covered, we can achieve the proportion of red channel with as high as 0.81. But it's partially covered, actually, you can see that it's not that high. So we can just using a simple threshold method to detect whether the camera lens is fully covered. Then we will proceed to the next step. Next, we design a gradient-based optimization scheme on the camera and flashlight configuration to mitigate the impact of the ambient light. We studied the pixel intensity by evaluating the light intensity change during each of the cardio cycle, and specifically, we calculated the pixel-wide difference between two frames with maximum and minimal pixel average in red channel. Our preliminary results found that the maximum biometric sensitivity can always be found, so it motivates us to iteratively search all the different configurations to finally decide which configuration we will use to extract the cardiac wave in the following component. Okay, next, for the dynamic cardiac wave extraction, we first calculate the average of the frame in a cardiac cycle wave and then identify 2 frames that have the maximum and minimal average pixel value. The element-wise difference between these 2 frames is then calculated, and we select the pixels with sufficient high difference. So there will only partial of the pixels on the frame we will choose. That will also reduce the overload when we calculate the frames, calculate the cardiac wave. Then we use the pixel average to derive the cardiac wave. In particular, the cardiac wave will derive based on the selected pixels. We will also adaptively update it for each of the following cardiac cycles. So you keep changing to adapt to the environmental ambient light change. So next, we extract, based on the derived cardiac wave, we extract 30 systolic and dystolic features directly from the cardiac wave to characterize the cardiac motion. We first locate the inflation point, as shows here, the SP, DP, or DN. These are the inflation point by searching for the local minimal and maximal within each of the cardiac cycle. The normalized time interval and the normalized amplitude values will be used as the fiducial features. These features have been proven to invariant to emotion status, such as anxiety, nervousness, and excitement. We also propose to extract the non-fiducial features, which are more robust to subtle movement of fingertip. We pass the cardiac waves through 2 high-pass filters with cutoff frequency 1 Hz and 2 Hz. And then we obtain 2 non-fiducial cardiac waves. The normalized distance between the local minimal and the maximal on each of the cardiac cycle are unique to each individual. And together with the fiducial features we derived in previous step, will serve as features used to characterize the cardiac motion. As we know that the cardiac waves may have some scale variation from day to day, since we provide our feature transformation scheme to construct a reliable user profile and perform the user verification grounded on the primary component analysis. In particular, we find out that all the peoples actually share similar first several primary components after our process. So we will remove the first 2 primary components and select from the remaining primary component and construct a set of feature abstract we used to construct the user's profile. And then, we conduct the user verification through measuring the similarity between the newly captured cardiac abstracts and the profiled cardiac abstracts. In our experiment, we choose 17 cardiac cycles as the user's profile. It's a very small set of data set for storage saving. And then we will score the newly captured cardiac abstract through computing its average Euclidean distance from the user's profile. And finally, we'll give it the user verification result. Our system was implemented on iPhone 7, which actually have a high definition built-in camera with 12 megapixels and enables frame rate at 16 fps. And the data set we actually construct based on 12 participants and through single cardiac wave or cardiac cycle, we still can achieve over 95% accuracy. And as the cardiac cycle involved in the verification process increase, the accuracy will gradually increase correspondingly. So that indicates the robustness and accuracy with the system. And also we evaluated the effectiveness of different components we design, integrated in our system. First, we categorize our feature set into 3 different groups with fiducial feature only, non-fiducial feature only, and also the combined features. Finally, we found that finally, we evaluated the robustness of our system. You can see that as we introduced in previous slide, we only choose 17 cardiac sample waves as the user profile. 3 months,